Hello Internet, welcome back to our Voxel Terrain. In this video we are going to be opening up a box that I haven't opened in a while. Ever actually. We're going to be looking at compute shaders. So what I'm planning on doing is having a mask that you can actually use for destruction. So say you have like some scarring or some sort of crater. The idea is you're going to actually be able to do that in a single thing to modify this terrain. Right now we can just use circles, which I think I broke. Oh, aha, got it. That can go away. And that can come back. Sorry. Oh, what the heck? Stop going out of focus. So, I have tried to record this video a lot of times. That was actually a previous attempt that was causing this bug. I tried to do it all at once and just kind of throw compute shaders at this. That's a bad idea because I don't really understand them fully. So what we're going to start with is we're going to kind of introduce compute shaders here, and then the next video we're actually going to apply them to this. So we're really not going to touch our voxel terrain right now, which is a little bit unfortunate, but at the same time, this is going to kind of help us bring out a little bit more about what these actually are. So a shader is just a program. It's a really simple program. If we look at what we have so far, like we've got just these basic voxel shaders, and they just do either a fragment or a vertex shader. If we're doing a surface shader, that's just Unity doing it for us. But really all they do is they compute where the things go, which is the vertex shader, and then they compute what they look like, which is going to be the fragment shader. Compute shaders do exactly the same thing, which is they do really highly parallelized computing, but they don't necessarily get constrained to graphics. So we're going to mostly be working with render textures, but effectively what a compute shader lets you do is take a input stream and in parallel process that input stream and then give some output stream. So that's sort of what we're going to be working with. Like these are normal shaders. They're just basic. It's a surface shader, so you don't see the vertex shader. But we're just doing simple stuff like this. So if I go here and create a new compute shader, shader, compute shader, we can just create it like this, which is going to be our, I'm just going to call this the sample compute shader. And this is just so we can kind of introduce this. And you'll notice right off the bat, this looks totally different than this. There's a lot less of everything here. And that's by design. This should look a lot more like C, but it's almost like C is written in HLSL, which is the shader language. So what you get here is a few very important things. First, you get this pragma kernel CS main, and you'll note this CS main aligns with this one, which is the name of a function. And so what's happening here is this declaration is listing the number of functions, and you can actually have multiple of these in your shader code. So if I could type, we could do like foobar as another one, and as long as I have it defined somewhere, that's totally cool. You can have as many of these as you need in a single compute shader. You can't do that with these unless you do like separate passes. Here we'll actually be able to say, I want to call this function and give it this data. The next thing, we have our result. By default, Unity is just going to pass back a texture. So it's just going to render to a render texture. And that's going to be the result of our calculation. And then here is our main code. So we have the number of threads. There's a bunch of documentation on this, and this part, I struggled and tried to explain it last time because I don't really understand it. It didn't go well. I would recommend reading it. Effectively what this is doing is this is a 3-dimensional array of the number of threads. So since we have 8 times 8 times 1, we have 64 threads that are going to be running here. But it's more complicated than that because these textures are going to be bigger than that. And I'm not entirely sure how it all comes together. So I'll drop some links in the description. I would read those. At this point, I don't feel comfortable describing what this is because I'll probably be wrong. And so skipping over that a little bit, the next thing we have our function. This is just a standard function. It's going to be exactly like any other function. The declaration looks identical to something like this. We're just taking in an ID, which is going to be our dispatch thread ID. Focus. That actually worked. That was cool. So what we're doing is this ID is going to be the X, Y, and Z coming from not here, but it's actually going to reference the point in your texture. So effectively what this is doing is it is taking information and writing it to our result. So I'm actually going to leave all of this here. I don't think we need to change it. I'm not entirely sure how this is going to go, but we're going to work with it. So what I'm going to do is I'm going to call that function and render it out to a render texture that we're just going to create. And then we'll see what it does, and then we'll tweak it a little bit and kind of get a general understanding of how these things work. And then once we do that, the next video we're going to look into actually using streams so we can handle this a little bit more finely. So I'm just going to do a sample compute. Sure, that's a terrible name, but that's all right. And so I just need a public compute shader. So we just pass in the compute shader. And I think that's it. The other thing I want to do is have a render texture here. So we can actually render this out somewhere. And we'll just call this the result. So that's where we're going to render our shader. Then in the start, we need to do a few things here. We need first to actually find that function. So this works a little bit interestingly, since you can have multiple functions in your shader. Wrong thing, but you get the idea. Since you can have multiple of these, what ends up happening is you need to say what you're looking for. So we're going to do hold on, I've got it pulled up here. Compute.findKernel. So we're actually going to go and find what the name of that file is, or the ID of that function in the file. So we give it a compute shader and we say, I want CS main. And so the way this is going to work is it's going to return in an ID for whatever function has this, or it's going to fail out. We're not going to handle failures because I am bad. The next thing, we have our render texture as a result. I'm going to, hold on. For this, I'm actually referencing a few other tutorials. When I tried to do this before, I just kind of winged it. Turns out that's a bad idea. In some things it works. Hello, Windows. In some things it works, but for this, it really didn't. And so to avoid just wasting your guys' time, I'm trying to cut some of that. Granted, then I'd spend a minute talking about it, but anyway, what they're doing in their example is they actually create this render texture. We could actually do that. Let's just do that. So let's say result equals a new render texture. And we can actually just generate this. Let's make it 512 by 512. Is that what I need? No, I need a depth, 24. So we're making a 24-bit render texture. And we need the result to enable random read and write. This way we can actually write to it. If we don't do this, it's going to throw an error that we can't write to our textures. There's different optimizations Unity will do one way or the other, so we need to just handle that. And then finally, we're going to take our result and create it. So that will spin up a quick render texture and store it in a public value, so we should be able to still see it, but we don't need to do much else. And then there's two other things. We need to set the texture for our kernel, oops, and give it the result as our result texture. So let me show you what this is doing, because this is a little bit weird. So what we did is we took this result, matches up with our sample, not that, where'd it go? There we go, sample compute. It matches up with this texture, the read-write texture that we're actually writing to. So those two names have to be the same. And we're just mapping it to an actual object that we have knowledge of. My camera's being super weird. It's been being weird since the live streams. I don't know what's going on. Maybe it got a little bit hot. Not entirely sure. And then when we want to actually call this, all we have to do is dispatch it. So I call kernel, and then I give it the total dimensions, which is going to be the width of the texture divided by that number we had with the number of threads. So since it's 8 and 8, we're doing 8 and 8, and then just 1 for the Z because it's a 2D texture. We don't need to worry about that. So what this is doing is 512 times 8, and 512 times 8. I say times 8 because we have it here, which is multiplying it by 8. And so we're dividing down to get to the, so effectively we're creating a thread for every single pixel in this texture, and then we're just rendering it. So I should be able to just create an empty thing. I'm gonna disable everything but our camera, just for testing's sake, and pull over this sample compute and drop our compute chain on here. The render texture will be set as we go, but if I run this, we should get a result that looks like this, which is Sierpinski's triangle. That's interesting. So this is just the results of Unity's default texture, or Unity's default compute shader. So what this is doing, that's actually really interesting. I wasn't expecting that. I didn't know what this was actually going to result in. I read the tutorials and they all use this same example, just as kind of an intro, but none of them actually showed the render. So that's kind of cool. So apparently that's what this gets you, which is interesting. But what it's doing is giving you a red, green, and blue value. So if I just want a entirely red triangle, or an entirely red, I'm missing my words, an entirely red box, a render texture, this should get us that, and we should just be able to pass this in. So let's open this again, and we just get flat red. So effectively, at this point, we're not really gaining anything. This is effectively just a really weird way to do an image effect or something like that. But you can do a lot more. Like I said, there's like streams and things like that that you can work with to do this. And so the advantage of those streams is you're no longer working with graphics. So say you want to test if something like Prime or something, you can do that with these. They're better at certain things. It's still got all of the classic graphics stuff. So like branching logic is usually no-go. But you can do anything you feel like. Which I do not have any idea what I want to do. That was sort of like what I wanted to cover. there wasn't too much to it, because I wanted to keep this short, because I'm still learning this. A lot of my videos are kind of things that I'm still figuring out. So apparently doing that and that gets you Sierpinski's triangle. That I need to go and read up on some math because I don't understand how this is actually happening. It's cool. I think that's awesome. But I don't understand it. Okay, I'll do that on my own time. But anyway, what we have is a compute shader. It's taking, well, no input actually. Can we add input? I don't actually know. Let's try. So if I do like a float 4, let me check this. Oh, sure. Float 4 of color. If I want to just do something like this, does it work? So if I take a 4-dimensional float, which will just be RGBA, and pass that to our compute shader, can I just render this new triangle? So we'll do this times that times our color. And theoretically, we can get any color of Sierpinski triangle doing this, I think. Don't quote me on this. This may not work. But I'm thinking, just kind of free working on this by myself. If we plug in a color, I'll have to obviously specify it here. So public color. And let's actually move this down to our update. And the reason I'm doing that is because now that it's in our update, we can actually change this color in real time and it should update. We shouldn't need to do anything else. So what else do I need? We set our texture. Compute.set vector. Sure. And we're going to set color. Yeah, that's what I called it. And then color. I don't know if that works. Visual Studio is kind of trying to crash. That's cool. You okay there? There we go. So yeah, so color is accepted as a 4D vector. So we can plug that in. I don't know why it's not asking for the kernel here. I think that may just be, this is a higher level thing. Let's see here. Set factor, yes, that. So, if I'm correct, which I'm not entirely convinced I am, I should be able to start this. And select our game object. Right now it's just black, which is boring, but if I scroll up to red, we get red. If I change this to, say, blue, we should get blue. So yeah. So what we're doing is we're passing in values. Again, this is still basic level, but we're passing in a value to our shader, and then using that to compute the results. We're still getting graphics, so this feels a lot like a normal shader. But again, the cool thing with this is you can do more than you would be with a normal graphics. You can simulate physics if you need to, or anything else that's if it's handled with floating point math and can be multi-threaded, this could be a good way to do it. What I'm planning on doing, let me bring everything back. So what I'm planning on doing is currently, when we do destruction, so when I insert into this, what happens is every single one of these points gets evaluated for position from our mouse click. If I calculate every single cube at the same time, I can do that all multi-threaded and have the GPU effectively just calculate the distance and do a distance calculation and either return true or false. or even calculate what the results are, and we can actually use that in our shader. We don't to actually compute the difference. Instead of having to do like circles, I imagine that'll probably lead to some significant speed up. So that's where we're going. I have rambled for far too long, so I'm sorry for that. And I'm also sorry for leaving this Voxel Terrain for so long. I know a lot of you really like this series. It just learning this has taken a long time, just because I haven't had as much time as I wanted, and because I've been doing other things. But hopefully, by the end of the week, we are going to have destruction that is done in these shaders, so we can actually do like explosion scattering effects all with a single pass. And I think that's going to be super cool. Theoretically, I think we could probably get most of this to be calculated on the GPU, actually. Because everything is happening in these separate little squares. And I think if we moved each of those squares to their own separate thread, I don't think we lose anything. So maybe we'll take it there. I don't know how much further it's worth going. A lot of this is getting into like very specific implementations that you guys may need or may not need. So if there's something specific you guys are looking for, let me know in the comments and I can certainly look into it. Otherwise, we'll just kind of go where we go. So yeah. If there's anything you guys want to say or anything you guys want to see, let me know. If there's any improvements you think I can make, I'd love to hear those, because that's how I get better. So yeah, till next time, see you, internet.